All right, so here's one that's a little bit more complex. The ones I've been doing so far were based off of old homeworks, so they're not too hard. But if you need something even more complex than this, let me know. Uh, this one also has a problem that is below me in the description. So pause, read that if you haven't already, and yeah, okay, then I'll start it. So this one is more complex than just salt and water. It's multiple different things going into a system and combining, which does make it look a little bit more complex and hard to wrap your head around. But whenever there's more than one component going to a system and coming out, the goal at that point is to isolate it on a component by component basis in your mass balance in order to solve for the variables that you need to. So it'll look harder, but a lot of the time it's actually easier. Or maybe not easier, but it's easier than it looks. It's easier in the sense that once you isolate everything, it starts to look like the previous one that I put up. So we have 3 flows going into a system. I'm going to call these flow 1, flow 2, flow 3, into your system. And then you have whatever coming out. So the first one is your media. We have media going in. We don't know the concentration really. For now, we're just going to say that it is C1, and you'll see why I'm doing that later. But the flow for this one is 1 mil per minute. The second one is the potassium chloride, KCl, which is 100 millimole, and we do not know the flow rate for that one. Flow is we don't know. And then the last one is water, which there's no mass balance for water. Water's water. The concentration for everything for this is going to be 0, since the goal of putting the water in is just to dilute whatever's in there. So for water, we're just going to put 0 where we normally put concentration, and flow we're going to put another question mark, since we do need to know that. And then our final solution, the media, all we know about the media is that it's 1/3 of its initial concentration. So it's going to be 1/3 C1, hence why I just put C1 up here, since we don't need to know the exact molarity or anything like that of the media in terms of the problem, which you'll see in a bit. There may be problems in the future where you need to know things like that, but media is kind of like water in that it's not a concrete chemical, so you can't really say that it's like 200 millimole media or something. Like that's not how that works. So media is just media. For the potassium chloride, we know it's 20 millimolar. And then for the flow, we also don't know. So where do we start? There's a lot going on here. One thing that jumps out at me personally is that we have a relationship between flow 1 and the outflow, which is, I'm going to call this flow out right here, actually. We have a relationship. We have that the media is being diluted to 1/3 its original concentration, which means that whatever amount of media is coming through here is being diluted 3 times. 3 times in that the flow here whatever's coming out should be, the total volume should be 3 times this. So first we are going to find F out. That'll be part 1. So we establish that our C1, F1, because we are only doing this in terms of the media. These other two have zero media in them. So even if we did do C1, F1, C2, F2, all that, they would cancel out because there's no media whatsoever. So what we're left with is just, in terms of media, is just C1, F1 is equal to C out, F out. And here we have C1 and then F1. We know F1, it's up here, but so I'm just gonna put F1 for now. That is equal to C out, which is just 1/3 C1, and then F out. And then from here, you rearrange the equation to where it's F out is equal to, F out is going to be equal to 3 times the C1s cancel out because you're going to be dividing by C1. So it's just going to be 3 times F out. So, no, not F out, the F1. So F out is equal to 3 mils per minute. So that's part 1. So from here, once we have that, now that we have F out, we're able to find, so from here we still have 2 unknowns, and it's the 2 unknowns the problem asks for, and that's the flow of KCl and the flow of water. So from here, water isn't characterized by any sort of, there's no concentration or anything like that we can use, so we're going to do that last. But potassium chloride does. So we're going to do another mass balance equation, but in terms of potassium chloride. It's going to be the same as the others, where the others have no potassium chloride, so even if we wrote them down, they cancel out to be 0 anyways. So when you do it in terms of that, it's going to be, so find F2. It will come out to C2, F2 is equal to C out, F out. Yeah, we know the concentration of both, and we know the flow of this, so we're going to isolate F2 algebraically. So F2 becomes C out, F out over C2. And if it's a little confusing using C out multiple times, you could put C out parentheses media for this one, and then C out parentheses KCl if it makes things easier. If you were doing this in a program like we used to use, like MathCAD, you would have to do that. So because the system wouldn't be able to process it otherwise. I recommend doing that if you're not very good at tracking variables. But yeah, we know these 3, and if you solve for it, F2 comes out to 0.6 mils per minute. All right, and then from there, all we need is the flow of the last one. And that one's easy because all you have to do is add up all the flows, because the flow rates are going to be conserved. The total volume is going to be conserved. So find F3, it's just the total going in equal to the total going out. So F1 plus F2 plus F3 is equal to F out. Isolate F3, that's equal to F out minus F1 minus F2. So F3 becomes 1.4 mils per minute. Yeah, and there you go. So the way that these kinds of problems work, when you have multiple things going in and out, sometimes could be a little bit more complicated when you have a more bioprocessing specific problem. Like I know a problem you guys got in class recently has a lot of stuff specific to bioprocessing. It's a depth filtration problem. So the important thing is to not get lost in the amount of things that are being laid out, and to just write everything out, what's going in and what's going out, and try to calculate what those concentrations are or figure out what they are. And then from there, just don't get overwhelmed, put that down, start establishing relationships that you think would be relevant to finding what you need to find, and then from there, solving. But realistically, these kinds of problems are about parsing out the information, just laying out what you know and what you need to know, and then establishing some mathematical relationships, whatever you can surmise from what you have, and then going from there. But yeah, that's about it.